Hi students, this is Alex here. In this video, we are going to verify Gauss divergence theorem for the given f vector over the cylindrical region bounded by x square plus y square is equal to 9, z is equal to 0 and z is equal to 2. Let's write the Gauss divergence theorem, which is double integral over the surface S f vector dot n cap ds is equal to triple integral over the volume V del dot f vector dv. Now let's construct the diagram. We take three-dimensional axis, x-axis, y-axis and z-axis, which is mutually perpendicular, and we name it here x, y and z. And there is a unit vector I cap along the x-axis, j cap along the y-axis and k cap along the z-axis. Now coming to the equation, we have x square plus y square is equal to 9. So this is a circle. So let's take this equation here. X square plus y square is equal to 9 is 3 square. So its center is 0, 0 and radius is 3. So we have a circle with the center origin and radius 3 units, something like this in the xy plane. So this is our origin, and this point, if I take it as A, it is meeting at a distance of 3 from the origin. So 3, 0, 0 because this is a radius. This is a point B, which is 0, 3, 0. And this is Z is equal to 0. This is a plane equation, Z is equal to 0. And now we have another circle at Z is equal to 2. So which is of the same size at 2 units. So the circle will be something like this, and this is the region where it meets the z-axis at 2, and if I join this, we get a complete cylinder. This is our cylinder, and this top surface equation is z is equal to 2 because it meets at a point 2 here. Now coming to the left hand side of the Gauss divergence theorem, it is double integral over the region over the surface S f vector dot n cap ds. But we have three surfaces. One is double integral this bottom surface f dot n cap ds, then we have double integral top surface, which is f dot n cap ds, then we have the curved surface surrounding region, which is once again f vector dot n cap ds. Now coming to the first part, I1, which is the bottom surface, and it is f dot n cap ds. We have double integral f dot n cap is nothing but f dot, and in the bottom surface we have the n vector, which is going in the downward direction, which is exactly opposite to that of the k. This is the n cap. N cap is a unit vector perpendicular to the surface moving away from that area. So it is opposite to that of k. So it is minus k cap, and this is having the dimension of x and y, which we can see from the diagram. This is the x value and this is the y value. So it is having the region area x and y. So we take this as dx and dy. So I have to take the x limit. The x limit varies from here to here, and this is the equation. From this, the value of x is equal to root of 3 square minus y square, and here it is x is equal to root of 3 square minus y square, but this part of x is minus and this part of x is plus. So it varies from minus root of 3 square minus y square, and this is from root of 3 square minus y square, and y varies from minus 3 to plus 3, that we can see from the diagram. This is the minus 3 and this is plus 3. Now f dot minus k cap, this is our f vector dot k cap. If I put only z square will come, and there is a minus sign, so minus z square. So double integral minus z square dx dy will come, and the rest of the limits we have to write as it is. But in this region, the equation of the plane is z is equal to 0, that already we have mentioned here. So when I replace z as 0 here, the entire value becomes 0. So first part is 0. Now coming to the second part, I2, this is a top surface. The bottom surface z is 0, top surface z is equal to 2. So same thing I have to write it again. In I2 we have double integral minus root of 3 square minus y square to root of 3 square minus y square. This is from minus 3 to plus 3. F dot k cap dx dy, because in the top surface, this is our top surface and n cap is pointing upward, which is along the direction of k. So when we do f dot k, we get only z square, and equation of the plane is z is equal to 2 here. So this part now becomes double integral z square dx dy, and value of z is 2. This is from minus root of 3 square minus y square to root of 3 square minus y square. This is from minus 3 to plus 3. When we substitute z as 2 here, it becomes 2 square 4. So 4 can be taken outside. Now we have double integral dx dy. This is minus root of 3 square minus y square to root of 3 square minus y square, minus 3 to plus 3. Now this part of integration we are going to evaluate first, which is with respect to x. So this will become 4 integral minus 3 to 3. Its integration is only x alone, and limit varies from minus this value to plus this value into dy. Now coming to the substitution, we get upper limit, which is root of 3 square minus y square. When I put lower limit, minus of minus, it becomes plus root of 3 square minus y square into dy. Now this becomes 2 times, and the 2 can be taken out. So 4 2s are 8. Integral minus 3 to 3 root of 3 square minus y square dy. This part of the integration, we have a formula. Integral root of a square minus x square dx is x by 2 root of a square minus x square plus a square by 2 sine inverse x by a plus c. Here we have limit, so we don't put plus c. So we have 8 bracket open y by 2 root of 3 square minus y square plus 3 square by 2 sin inverse y by 3, from minus 3 to plus 3. When I put the upper limit, the first term becomes 0 and the second term becomes 3 square by 2 sin inverse 3 by 3. When I put the lower limit, again the first term becomes 0, then plus 3 square by 2 sin inverse minus 3 by 3. Then this is 8 into 3 square by 2 sin inverse 1, and there is a minus sign and there is a minus sign outside, so plus 3 square by 2 sin inverse of minus 1 becomes sin inverse 1 because of there is a minus sign outside. Now this is 2 times, so 8 into 2 into 3 square by 2 sin inverse 1 is pi by 2. So we can cancel this and we can cancel this also. So 3 square is 9, 9 4, 36 pi. Now we have the third part, which is the curved surface area. So here we have written, let's write it down. So I3 is double integral, we have f vector dot n cap and ds, and we have the curved surface. And in the curved surface, we are going to consider the surrounding and we are going to take n cap along in this direction, that is the perpendicular to the YZ plane. So it will be something like this. This is our n cap for this curved surface. So let's find n cap separately first, which is del phi by mod of this, and phi is nothing but they gave the circle equation x square plus y square equal to 9. From this we take x square plus y square minus 9. So now del phi is nothing but I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z of this x square plus y square minus 9. So coming to the first part, it is 2x I cap and the rest of the things will be 0. Coming to the second part, it will become 2y j cap and third part is 0. Now from this we can take 2 common, so xi cap plus y j cap, and magnitude of this will be 2 root of x square plus y square, but from the given circle equation x square plus y square is 9, so we can substitute that. So 2 root 9, which is 2 into 3, which is 6. Now n cap becomes 2 into xi cap plus y j cap whole divided by 6. So we can cancel this, it becomes 3. So it is xi cap plus y j cap divided by 3. So now we are going to substitute in this f dot n cap ds. So this will be double integral f vector dot xi cap plus y j cap by 3 ds. And in the question they have given, this is our f vector. When we do dot product with this, corresponding I and I if I do, it is xy, then again plus yx. So it is again xy only, whole divided by 3. Then we have ds. So we are going to take ds on yz plane. So when we take ds along the yz plane, so this n cap is along the I cap. So now ds becomes dy dz divided by n cap into I cap. So ds becomes dy dz by n cap dot I will become, when I do dot I with this, we get only x by 3. So this is x by 3. So finally ds is 3 by x into dy dz. So we are considering the n cap for this curved surface along the yz plane, perpendicular to yz plane. So it is along the I cap. So we have ds formula as dy dz by n cap dot I cap. So we have to substitute that in place of ds here. So we have double integral, already 2xy we got here by 3, and this is 3 by x dy dz. So we can cancel this x and x, 3 and 3, 2 is a constant which we can take it outside. And here the limit of y varies from minus 3 to 3, and the limit of z varies from this bottom to top, that is 0 to 2. So here we have from 0 to 2. So now coming to the integration of this, we are going to evaluate this with respect to y first. So 0 to 2, integral minus 3 to 3, 2 can be taken out. We have y dy dz. So first integration is with respect to y. So it is y square by 2. So 2 integral 0 to 2 y square by 2, and limit varies from minus 3 to plus 3 dz. When we substitute the upper limit 3, 3 square 9 by 2, then minus, when you put the lower limit, minus of 3 square is plus 9. So 9 by 2. The rest of the terms are written as it is, but here 9 by 2 minus 9 by 2 becomes 0. So the total answer is 0. Now total LHS, we have top surface. Sorry, first we calculated the I1 bottom surface, which is 0. Then I2 is the top surface, which we calculated as 36 pi. And the last part is 0. So total LHS is 36 pi. Now coming to the RHS part of the Gauss divergence theorem, we have triple integral over volume del dot f vector dv. Now this is triple integral over the volume. Del is I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z dot of f vector, which is taken from the question, and into dv. dv is dx dy dz. Now triple integral over volume, and when I do dot of I dot I, and it will become y, and differentiation with respect to partial derivative with respect to x is 0. First term is 0. When I do j dot j, and again that becomes 0, and the last part is only z square. Dou by dou z of z square is 2z. Now we have dx, dy, dz. And now we have to use a limit. So 2 is a constant, can be taken out. We have triple integral z dx, dy, dz. X varies from minus root of 3 square minus y square to root of 3 square minus y square, and y varies from minus 3 to plus 3, z varies from 0 to 2. That we can see clearly from the diagram. That is, x varies from minus of this to plus of this, and y varies from, if I take y from this, by taking x as 0, we get y is equal to plus or minus 3, and z is varying from 0 to 2. So now we are going to integrate this first with respect to x. Means we have z as a constant and we have only x, and limit is from minus of this value to plus of this value. Then integral minus 3 to 3, integral 0 to 2, 2 times dy dz. When I substitute the limit, upper limit minus of minus lower limit, so it becomes plus. So z into 2 times of root of 3 square minus y square. Upper limit minus lower limit, but already lower limit is having a minus value. So we have dy dz, integral minus 3 to plus 3, 0 to 2, 2 times. Now once again, this 2 can be taken outside and it becomes 4. So 4 integral 0 to 2, integral minus 3 to plus 3. Now z is a constant. We are going to integrate this term with respect to y. So we are going to integrate with respect to y using the formula, and z will be written as it is. This formula is y by 2 root of 3 square minus y square plus 3 square by 2 sin inverse y by 3, and our limit is from minus 3 to plus 3. Still we have dz, and outside we have 0 to 2, 4 times. When I substitute the upper limit, the first part becomes 0. Second part, this becomes sin inverse 3 by 3, which is sin inverse 1, which is pi by 2. So 3 square by 2 into pi by 2. And when I put the lower limit, again the first part is 0 plus 3 square by 2 into sin inverse minus 1 is minus pi by 2. Bracket close, dz. Now this becomes 4 integral 0 to 2 z into, this is 9 pi by 4, again minus or minus, it becomes plus 9 pi by 4 dz. So which is 18 pi by 4. So 4 into 18 pi by 4 is taken common, 0 to 2 z dz. So now we are going to integrate this z square by 2, limit is from 0 to 2, and outside we have 18 pi. We put the upper limit 2 square 4, 4 by 2 lower limit is 0, and we have 18 pi. This is 2 times, so totally 36 pi. So we got LHS also 36 pi and RHS also 36 pi. Hence Gauss divergence theorem is verified.